In mathematics, mixing is an abstract concept originating from physics. The attempt to describe the irreversible thermodynamic process of mixing in the everyday world. Mixing paint, mixing drinks, etc. The concept appears in ergodic theory, the study of stochastic processes and measure-preserving dynamical systems. Several different definitions for mixing exist, including strong mixing, weak mixing and topological mixing, with the last not requiring a measure to be defined. Some of the different definitions of mixing can be arranged in a hierarchical order. Thus, strong mixing implies weak mixing. Furthermore, weak mixing, and thus also strong mixing, implies ergodicity. That is, every system that is weakly mixing is also ergodic. And so one says that mixing is a stronger notion than ergodicity. Mixing in stochastic processes. Let x t equals opening curly bracket x t minus 1 x t plus 1 closing curly bracket. Display style langle x underscore t rangle equals l dots x underscore t1 x underscore t plus 1 l dots be a sequence of random variables. Such a sequence is naturally endowed with a topology. The product topology. The open sets of this topology are called cylinder sets. These cylinder sets generate a sigma algebra. The Borel sigma algebra. It is the smallest, coarsest, sigma algebra that contains the topology. Define a function, alpha, s. Display style, alpha, s. Closing curly bracket, called the strong mixing coefficient, as, alpha, s. Sup, opening curly bracket, pipe, p, a, b, minus, p, a, p, b, pipe, minus, infinity, less than, t, less than, infinity, a, element of, x, minus, infinity, t, b, element of, x, t, plus, s, infinity, closing curly bracket, display style, alpha, s, equivalent, sup, left p, a, cap b, p, a, p, b, pipe, and fd less than t less than, and fd, a, in x underscore, and fd, caret, t, b, in x underscore, t plus s, caret, and fd, right. Closing curly bracket. In this definition, p is the probability measure on the sigma algebra. The symbol, x, a, b, display style x underscore, a, caret, b, with, minus, infinity, a, b, infinity, display style, and fd, leq a, leq b, leq, and fd, denotes a subalgebra of the sigma algebra. It is the set of cylinder sets that are specified between times a and b. Given specific, fixed values, x, a, plus 1, display style x underscore a plus 1, etc., of the random variable, at times, a, display style a plus 1, display style a plus 1, etc., then it may be thought of as the sigma algebra generated by opening curly bracket, x, a plus 1, x, b, closing curly bracket, display style, x underscore a plus 1, l dots, x underscore b, closing curly bracket, the process, x, t, display style, langle x underscore, t, rangle, is strong mixing if, alpha, s, 0, display style, alpha, s, to 0, as, s, infinity, display style s2, and fd, One way to describe this is that strong mixing implies that for any two possible states of the system, realizations of the random variable, when given a sufficient amount of time between the two states, the occurrence of the states is independent. Types of mixing. Suppose XD is a stationary Markov process with stationary distribution Q. Denote L2 Q. Display style L caret 2 Q. Closing curly bracket. The space of Borel measurable functions that are square integrable with respect to measure Q. Also let E T phi x equals E phi x T x 0 equals x. Display style mathcal E underscore T var phi x equals operator name E var phi x underscore T mid x underscore 0 equals x. Closing curly bracket. Denote the conditional expectation operator on L2 Q. Display style L caret 2 Q. Closing curly bracket. Finally, let Z equals opening curly bracket phi element of L2 Q phi D Q equals 0. Closing curly bracket. Display style Z equals left var phi in L caret 2 Q int var phi dq equals 0 right. Denote the space of square integrable functions with mean 0. The row mixing coefficients of the process XD are rho t equals sup phi element of Z phi 2 equals 1 e t phi 2. Display style rho underscore t equals sup underscore var phi in Z backslash var phi underscore 2 equals 1 mathcal E underscore T var phi underscore 2. Closing curly bracket. The process is called row mixing if these coefficients converge to 0 as t infinity, and row mixing with exponential decay rate if rho t less than e minus delta t for some delta greater than 0. For a stationary Markov process, the coefficients rho t may either decay at an exponential rate, or be always equal to 1. The alpha mixing coefficients of the process XD are alpha t equals sup phi element of Z phi infinity equals 1 e t phi 1. Display style alpha underscore t equals sup underscore var phi in Z backslash var phi underscore and d equals 1 mathcal E underscore T var phi underscore 1. Closing curly bracket. The process is called alpha mixing if these coefficients converge to 0 as t infinity. It is alpha mixing with exponential decay rate if alpha t less than gamma e minus delta t for some delta greater than 0. And it is alpha mixing with sub-exponential decay rate if alpha t less than xi t for some non-increasing function xi t satisfying t minus 1 lane xi t 0 as t infinity. The alpha mixing coefficients are always smaller than the rho mixing ones. Alpha t rho t. Therefore, if the process is rho mixing, it will necessarily be alpha mixing too. However, when rho t equals 1, the process may still be alpha mixing with sub-exponential decay rate. The beta mixing coefficients are given by beta t equals sup 0 phi 1 pipe e t phi x minus phi d q pipe d q. Display style beta underscore t equals int sup underscore 0 leq var phi leq1 left mathcal E underscore T var phi x int var phi dq right dq closing curly bracket. The process is called beta mixing if these coefficients converge to zero as t infinity. It is beta mixing with exponential decay rate if beta t less than gamma e minus delta t for some delta greater than 0. And it is beta mixing with sub-exponential decay rate if beta t xi t 0 as t infinity for some non-increasing function xi t satisfying t minus 1 lane xi t 0 as t infinity. A strictly stationary Markov process is beta mixing if and only if it is an aperiodic recurrent Harris chain. The beta mixing coefficients are always bigger than the alpha mixing ones. So if a process is beta mixing, it will also be alpha mixing. There is no direct relationship between beta mixing and rho mixing. Neither of them implies the other. Mixing in dynamical systems. A similar definition can be given using the vocabulary of measure-preserving dynamical systems. Let x a mu t display style x mathcal a mu t closing curly bracket be a dynamical system, with t being the time evolution a shift operator. The system is said to be strong mixing if, for any a b element of a display style a b in mathcal a, one has lim n infinity mu a t minus n b equals mu a mu b display style lim underscore n 2 and d mu left a cap t caret n b right equals mu a mu b closing curly bracket. For shifts parametrized by a continuous variable instead of a discrete integer n, the same definition applies, with t minus n display style t caret n replaced by t g display style t underscore g, with g being the continuous time parameter. To understand the above definition physically, consider a shaker m display style m full of an incompressible liquid, which consists of 20% wine and 80% water. If a display style a is the region originally occupied by the wine, then for any part b display style b of the shaker, the percentage of wine in b display style b after n display style n repetitions of the act of stirring is mu t n a b mu b display style frac mu left t caret n a cap b right mu b closing curly bracket closing curly bracket closing curly bracket. In such a situation, one would expect that after the liquid is sufficiently stirred, n infinity display style n2 and d every region b display style b of the shaker will contain approximately 20% wine. This leads to lim n infinity mu t n a b mu b equals mu a mu m equals mu a display style lim underscore n right arrow and d frac mu left t caret n a cap b right mu b equals frac mu a mu m equals mu a closing curly bracket, where mu m equals 1 display style mu m equals 1, because measure-preserving dynamical systems are defined on probability spaces, and hence the final expression implies the above definition of strong mixing. A dynamical system is said to be weak mixing if one has lim n infinity 1 n k equals 0 n minus 1 pipe mu A T minus K B minus mu A mu B pipe equals 0. Display style lim underscore n 2 and d frac 1 n sum underscore k equals 0 caret n 1 left mu A cap T caret K B mu A mu B right equals 0. Closing curly bracket. In other words, T display style T is strong mixing if mu A T minus n B minus mu A mu B 0. Display style mu A cap T caret n B mu A mu B to 0 in the usual sense. Weak mixing if pipe mu A T minus n B minus mu A mu B pipe 0. Display style left mu A cap T caret n B mu A mu B right to 0. Closing curly bracket. In the Cesaro sense. And ergodic if mu A T minus n B mu A mu B display style mu left A cap T caret n B right 2 mu A mu B closing curly bracket in the Cesaro sense. Hence, strong mixing implies weak mixing, which implies ergodicity. However, the converse is not true. There exist ergodic dynamical systems which are not weakly mixing, and weakly mixing dynamical systems which are not strongly mixing. For a system that is weak mixing, the shift operator T will have no non-constant, square integrable eigenfunctions with associated eigenvalue of 1. In general, a shift operator will have a continuous spectrum, and thus will always have eigenfunctions that are generalized functions. However, for the system to be, at least, weak mixing, none of the eigenfunctions with associated eigenvalue of 1 can be square integrable. L. 2. Display style L caret 2. Formulation. The properties of ergodicity, weak mixing and strong mixing of a measure-preserving dynamical system can also be characterized by the average of observables. By von Neumann's ergodic theorem. Ergodicity of a dynamical system. X. A. Mu. T. Display style. X. Mathcal. A. Mu. T. Closing curly bracket. Is equivalent to the property that, for any function, f, element of, L, 2, x, mu, display style f in L caret 2, x, mu, closing curly bracket, the sequence, f, t, n, 0, display style, f, circ t caret n, underscore, n, geq 0. Converges strongly and in the sense of Cesaro to x, f, d, mu, display style, int underscore, x, f, d, mu, I, e, lim, n, infinity, 1, n, equals, 0, n, minus, 1, f, t, n, minus, x, f, d, mu, L, 2, x, mu, equals, 0. Display style, lim underscore, n, 2, and d, left 1, over n, sum underscore, n equals 0, caret, n 1, f, circ t caret, n, int underscore, x, f, d, mu, right, underscore, L caret, 2, x, mu, equals 0. Closing curly bracket. A dynamical system, x, a, mu, t, display style, x, mathcal, a, mu, t, closing curly bracket, is weakly mixing if for any functions f, display style f, and g, element of L, 2, x, mu, display style g in L caret 2, x, mu, closing curly bracket, lim, n, infinity, 1, n, n, equals, 0, n, minus, 1, pipe, x, f, t, n, g, d, mu, minus, x, f, d, mu, x, g, d, mu, pipe, equals, 0. Display style lim underscore n 2 and d 1 over n sum underscore n equals 0 caret n 1 left int underscore x f cert t caret n c dot g d mu int underscore x f d mu c dot int underscore x g d mu right equals 0. Closing curly bracket. A dynamical system x a mu t display style x mathcal a mu t closing curly bracket is strongly mixing if for any function f element of L 2 x mu display style f in L caret 2 x mu closing curly bracket the sequence f t n n 0 display style f cert t caret n underscore n geq 0 converges weakly to x f d mu display style int underscore x f d mu closing curly bracket I e for any function g element of L 2 x mu display style g in L caret 2 x mu closing curly bracket lim n infinity x f t n g d mu equals x f d mu x g d mu display style lim underscore n 2 and d int underscore x f cert t caret n c dot g d mu equals int underscore x f d mu c dot int underscore x g d mu closing curly bracket. Since the system is assumed to be measure preserving, this last line is equivalent to saying that lim n infinity cov f t n g equals 0 display style lim underscore n 2 and d operator name cov f cert t caret n g equals 0 closing curly bracket, so that the random variables f t n display style f cert t caret n and g display style g become orthogonal as n display style n grows. Actually, since this works for any function g display style g closing curly bracket, one can informally see mixing as the property that the random variables f t n display style f cert t caret n and g display style g become independent as n display style n grows. Products of dynamical systems. Given two measured dynamical systems x mu t display style x mu t closing curly bracket and y nu s display style y nu s closing curly bracket, one can construct a dynamical system x times y mu nu t times s display style x times y mu o times nu t times s closing curly bracket on the Cartesian product by defining t times s x y equals t x s y. Display style t times s x y equals t x s y. Closing curly bracket. We then have the following characterizations of weak mixing. Proposition: a dynamical system x mu t display style x mu t closing curly bracket is weakly mixing if and only if, for any ergodic dynamical system, y nu s display style y nu s closing curly bracket, the system x times y mu nu t times s display style x times y mu o times nu t times s closing curly bracket is also ergodic. Proposition: a dynamical system x mu t display style x mu t closing curly bracket is weakly mixing if and only if x 2 mu t times t display style x caret 2 mu o times mu t times t closing curly bracket is also ergodic. If this is the case, then x 2 mu t times t display style x caret 2 mu o times mu t times t closing curly bracket is also weakly mixing. Generalizations. The definition given above is sometimes called strong 2 mixing, to distinguish it from higher orders of mixing. A strong 3 mixing system may be defined as a system for which lim m n infinity mu a t minus m b t minus m minus n c equals mu a mu b mu c. Display style lim underscore m n 2 and d mu a cap t caret m b cap t caret m n c equals mu a mu b mu c. Closing curly bracket holds for all measurable sets A, B, C. We can define strong K mixing similarly. A system which is strong K mixing for all K equals 234 is called mixing of all orders. It is unknown whether strong 2 mixing implies strong 3 mixing. It is known that strong M mixing implies ergodicity. Examples: irrational rotations of the circle, and more generally irreducible translations on a torus, are ergodic but neither strongly nor weakly mixing with respect to the Lebesgue measure. Many map considered as chaotic are strongly mixing for some well-chosen invariant measure, including the dyadic map, Arnold's cat map, horseshoe maps, Kolmogorov automorphisms, the geodesic flow on the unit tangent bundle of compact surfaces of negative curvature. Topological mixing. A form of mixing may be defined without appeal to a measure, using only the topology of the system. A continuous map f x x display style f x 2x is said to be topologically transitive if, for every pair of non-empty open sets A, B, X, display style A, B, subset X, there exists an integer n such that f n A, B does not equal display style f caret n A cap B n eq var nothing, where f n display style f caret n is the nth iterate of f. In the operator theory, a topologically transitive bounded linear operator, a continuous linear map on a topological vector space, is usually called hypercyclic operator. A related idea is expressed by the wandering set lemma. If X is a complete metric space with no isolated point, then F is topologically transitive if and only if there exists a hypercyclic point x, element of x, display style x, in X. That is, a point x such that its orbit, opening curly bracket, F, n, x, n, element of n, closing curly bracket, display style F caret n, x, n, in mathbar n, is dense in X. A system is said to be topologically mixing if, given open sets, A, display style A, and B, display style B, there exists an integer n, such that, for all n greater than n, display style n greater than n, one has f n a b does not equal display style f caret n a cap b neq var nothing, closing curly bracket. For a continuous time system, f n display style f caret n is replaced by the flow phi g display style var phi underscore g, with g being the continuous parameter, with the requirement that a non-empty intersection hold for all g greater than n display style vert g vert greater than n. A weak topological mixing is one that has no non-constant continuous with respect to the topology eigenfunctions of the shift operator. Topological mixing neither implies, nor is implied by either weak or strong mixing. There are examples of systems that are weak mixing but not topologically mixing, and examples that are topologically mixing but not strong mixing.